In this video, we are going to explore the idea of the 3D coordinate system. So we remember in 2D, we have our XY coordinate system. We've seen it so many times that you could most certainly draw it in your sleep. But if we want to extend this idea to 3D, we draw it a little differently. So we actually let this one that looks like it's headed kind of out towards us to be the positive X direction. This one right here to be the positive Y direction, and then straight up will be our positive Z direction. This is the standard way to draw a 3D coordinate system, although you certainly can draw it a different way as long as you orient it and label it and let your reader know. But this is pretty standard way to draw it. Alright, so if we wanted to plot a point in 3D, we would do it in a very similar way. Let's say we wanted to plot the point x1, y1, z1. So we would travel a certain distance along the x-axis. We'll say an x1 distance. Travel a certain distance along the y-axis. We'll say y1 distance. And then travel straight up from there along the z-axis. We'll say z1. And that would be the point x1, y1, z1. So this is a point in 3 space. Very simple and easy to understand. We actually live in 3 space, but it is quite difficult sometimes to represent it in 2 space, as we will see in the coming videos. Alright, the first thing we want to establish is our distance formula in 3 space. Alright, so maybe we remember the distance formula in 2 space. So if we draw a quick little 2 space right here, so this is P and this is Q, and perhaps P has the coordinates x1, y1, and Q has the coordinates x2, y2, then if you remember the distance between PQ, which we will use those bars to represent the distance, is really derived from the Pythagorean theorem, right? The distance in the x values squared plus the distance in the y values squared, right? That's the sum of the legs of the triangle squared, and if we take the square root of it, that'll give us our hypotenuse C. And that is how we derive the distance formula in 2 space. Alright, so in order to do this in 3 space, we need to get a new board. So let's travel this way for 3D formula, and bear with me as I try to draw these. So first, we will draw our 3D coordinate system to help us orient ourselves. Remember X, Y, Z, and you should always label your graphs here just like you should have always labeled them in 2 space. Alright, I'm going to start by drawing a rectangle because I think that will be helpful. So we're actually going to draw, oops, let me redo that because I want this to be slanted like this. So it travels along the y-axis. I'm going to do another one here. We're going to connect, 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 connect. Okay, so let's label 2 points here in 3 space. We'll say this one right here we'll call P1, and we will label it X1, Y1, and Z1. And we'll label this point right here P2, and that'll be X2, oops, Y2, and Z2. Alright, and so we're going to be interested in finding the distance between those 2 points right there. So that's P2, and down there is P1. Perfect. Alright, so I'm going to let's consider 2 triangles. Because we're gonna split this case up into 2 space because that's a simpler case for us and we already know how to do it. So let's consider this first triangle right here, we'll do it in green, to be this one right here. So this is all taking place on this plane right here that has the same z value. All these points in this first triangle have the same z value, which is z1. So let's label this point right here. This point, so notice that it has the same x value as P2, so it's x2. It has the same y value as P1, and it has the same z value as P1. All right, so that means this distance right here is really just the difference in the x's. So we'll write that as x2 minus x1. Good. All right, let's label this point over here. This point, notice, has the same x value as P2, the same y value as P2, but it has the same z value as P1. All right, so this distance along this base of this triangle sitting in this plane is really just the difference in the y's, because the x's and the z's are the same. So this is y2 minus y1. All right, now let's label this hypotenuse here A. So what is A? Well, we know that it's the hypotenuse of this right triangle here. So A squared is really equal to x2 minus x1 squared plus y2 minus y1 squared. Right? That's our Pythagorean theorem in place. So A is just the square root of this. All right? Which is just our familiar distance formula in 2-space. All right, so now we're going to consider a new triangle. All right, and I'm going to draw this one in blue. It's also in 2-space, but it's floating out here at this angle. So consider this triangle right here. Okay, so it's like if you could tilt your head to the side, you could see it. So it would look like this. Except, I should be clear, its hypotenuse is actually the hypotenuse here that we are in search of. That's actually the distance we're looking for. So the bottom here is A, and then the height of this right triangle, if you see, is this distance between here and here. And notice it's really just the difference in the y's. So z2 minus z1. So this green distance here, which is really the distance between P1 and P2, right, is really the square root of A squared plus Z2 minus Z1 squared, right? That's that distance of that hypotenuse. Now, plugging in what we know A to be, let's go to a new board where we have more space, we actually can get the distance between P1 and P2 is the square root. I'm now going to plug in A squared, x2 minus x1 squared plus y2 minus y1 squared. There's my A squared right here. Plus z2 minus z1 squared. And this is our distance formula in 3